Hi, this lecture is a brief introduction to machine learning. For those of you who have taken courses in machine learning, you can safely skip this. This lecture is really for those people who have no background in machine learning but would still like to take the course. We're going to go through some of the very basics. I recommend strongly that you read up more on machine learning before you take the course, but let's just dive in. So we're going to cover what is machine learning, in particular what features are in machine learning. We'll talk a little bit about supervised machine learning and the models that we generate or train in supervised machine learning. Firstly, what is a feature? A feature is a specific thing in machine learning. It refers to a property of some entity or object that you want to make predictions with. So let's take the example of a fruit. And we have two fruits here, you can see, an apple and an orange. And let's try and predict whether it's an apple or an orange based on weight. Well, we can see that the average weight of an apple is between 70 and 250 grams, and the average weight of an orange is between 60 and 300 grams, so it's kind of going to be difficult to tell whether the fruit is an apple or an orange based solely on weight. If we try color, on the other hand, as a feature of apples, as in a feature of orange, we can see that the apple is green and the orange is orange. That might be a useful way to differentiate between the two fruits. So the feature is the piece of information, it's a condensed piece of information that will help us predict some, in this case, class of fruit. So whether it's an apple or an orange. So color is a feature of fruit, and we can see the color spectrum at the bottom of the slide. And what we'd like to do is to be able to train what we call a machine learning model to predict, given the color of a piece of fruit, whether it's an apple or an orange. So we call that the label. If we know that the fruit is an apple, we'll say that the label is apple for this piece of fruit. And if it's an orange, we'll say that the label is an orange for this piece of fruit. This is what we call supervised machine learning. We give the program an example of an apple. We say that the color is green. We give exactly the color. And then we tell the model this is a piece of training data. And we do the same with oranges. We say here's an orange, here's the color of the orange. We know it's an orange, so that's the label or the target, the thing we're trying to predict as well. And we give enough of these examples that the machine learning system is able to differentiate between them. So the examples that we give, we know that they're apples, we know the color, and we basically can use that then to help predict whether a new piece of fruit that we haven't seen before, whether it's going to be an apple or an orange. So this label, whether it's an apple or an orange, is what we call the target. That's the thing we're trying to predict. And the information we're using to try and make the prediction is the features, in this case, the fruit's color. Now, this is a little bit of an oversimplification because you know that color doesn't come in one number. I'm showing you a spectrum at the bottom, which is a little bit misleading because if you know much about colors, you'll know that typically in your monitor, in your computer, you've got red, green, and blue channels. So there's three colors effectively. And we can see that for the red channel, orange has on average 255 as its color number, whereas the green fruit has 0. And for the green channel, we can see green is at 128 on average, and orange is about 165. And on the blue channel, we have 0 for both fruits. So in fact, what we can do is we can differentiate between the apple and the orange, primarily on the red channel, and to a certain extent on the green channel. And we can draw a straight line between them, in fact, and we call this straight line a decision boundary. So it's a straight line that separates the apples from the oranges based on the red channel color and the green channel color. This is what we call a linear model. Let's have a look at this in a graphical form. So we're not interested in the blue channel, so we're going to ignore that. We're left with two features, the green channel and the red channel. So if we look on the y-axis, we have the green values from 0 to 255, and on the x-axis we have 0 to 255 on the red channel. And all of these small crosses that you can see here in the chart, the green ones represent, the circles are green, represent apples, and the pluses are orange, they represent the oranges. These are examples. So we have examples of oranges, and we can see if we take any given point there, so we can take a point here, for example, we can see that its red level is about around 200 or 180, and the green level is somewhere around 70. And this black line here was a decision boundary that a machine learning model trained. And it learnt. So the machine learning model knows that this is roughly the boundary between the red apples, the orange oranges and the green apples. So you can see that there's an area marked in red here where it's difficult to classify whether it's a green apple or an orange because they're kind of mixed in. For some reason, these examples of apples and oranges, they have green and red values that are quite similar to one another. So even this is a relatively large data set. So there's many examples of apples, green apples, many examples of oranges, and it's a bit mixed up. It's hard to get a very simple decision boundary, a linear straight line decision boundary that will separate the apples from the oranges. You can see here in this example, some oranges are on the left of the decision boundary. That means that the system would classify them as apples incorrectly. And then many of the oranges are in this area here, and they would also be incorrectly classified as apples. In fact, all of the apples in this example would be classified correctly. So it would be good for identifying if something is an apple, but then the problem is it might think it's an apple, but it's an orange. And if it says it's an orange, well, then you can see it probably is an orange because there's no apples on this side of the decision boundary. So let's look at some code to cover that example. So we can see a very simple piece of scikit-learn program here, a Python program, and it's implementing what we just talked about. We have two types of fruit. We have green apples, and they're represented by 0 for apples and 1 for oranges. And we can see we have 4 examples. We have 2 apples, so the label is set to 0 for the green apple, and then we have 2 oranges. 1 is set for the label when it's an orange. The actual examples of the fruit, the colors that we have, the first one is an apple, and it's set to 0 and 120. So 0 for the red channel, 120 for the green channel, 0 for the red channel, 110 for the green channel. There are apples, and then the 2 fruit examples we have are we have an orange where we've got 250 for the red channel, 150 for the green, 255 for the red, and 163 for the green. So these are our 4 pieces of fruit. The first 2 are apples, the second 2 are oranges. The labels tell us that. And now what we're going to do is train a machine learning model to learn that decision boundary. And we're going to use a decision tree classifier. You could use a logistic regression. There's many other machine learning algorithms out there you could use. We're not going to go into the details of which one is the best for which given example. In this example, we have way too few training examples. It's just a toy example to give you a feel for it. But what you do basically is we've given these features and these labels, and these are both lists, as you can see. We can pass them into our decision tree classifier object. We can call the fit method on them. So the fit method will train our model to learn this pattern. So it's going to take the input features, the labels, and it'll learn a pattern. So what we can do with this object CLF that we've just trained is we can use it to predict whether fruits we haven't seen before, we're going to call them test fruits, whether they are apples or oranges. So here are 2 test fruits. The first one we can see has a red channel of 0 and a green channel of 128. It's actually the test label. So we also know in advance whether it's an apple or an orange. It's actually an apple. And then the second example is an orange, and the label tells us this. So when we call clf.predict on the features, so we're asking the model, here's the input features. Please tell us what you think the labels are, the predicted labels. We're going to get back that list of predicted labels. Now this code is in the GitHub repo. If you run it, it will predict it correctly. So it's going to work. It's a very simple example, and the model is able to differentiate between the apples and orange in this case. Now, this problem of classifying whether a fruit is an apple or an orange is a little bit more difficult than the simplified model I just presented, because apples can also be red. So there's no straight line decision boundary between the apples and the oranges in this case, because we can see that, you know, the red apple is similar in that the blue channel is 0 for all 3 fruits. That's good. But it also has a red channel of around 255. And it differs a little bit from the orange in that the green channel tends to be 0, whereas in orange the green channel tends to be around 165. So if we were to, you know, introduce red apples into our classifier that we had earlier between the green apples and the oranges, we can see that it's no longer a straight line if we want to identify which fruit is an orange. You can see it's this, you know, squiggly line that sort of encompasses all of the oranges if we can learn that particular boundary. The apples are going to be located down here, so we couldn't just say, if we had the straight line, that every fruit on the right hand side of the decision boundary is an orange, because it may be an apple, of course, a red apple. So we would have to learn a decision boundary that's you can see is quite complex. So this isn't a linear classifier. Even if we had a lot of data, it's going to be a bit more challenging to learn this decision boundary. So we only looked at two colors. We looked at the green channel and the red channel. Somebody out there might say, well, hang on, can I not add some other feature to help us differentiate between apples and oranges? And the answer is, of course, yes. We had the weight that we saw earlier, and weight doesn't really help too much as a feature which predicts whether the fruit is an apple or an orange. But if you take another feature such as smoothness, now smoothness is, it's tactile in humans. We touch it and we know that apples are quite smooth and oranges are not so smooth. So if we could somehow measure smoothness, well, then we could differentiate between apples and oranges. Now, in fact, you can measure smoothness. It's not too difficult to do it now with imaging. So you could take an image of an apple and an orange, and you can infer the color through the image. But you can also have an estimate of the smoothness of it. So it's possible to estimate the smoothness of an apple or the fruit, whether it's an apple or an orange, and then use that as a feature to predict whether a new piece of fruit is an apple or an orange. And with three features, it gets a little bit harder to do the graph that we just saw. So we had an XY chart, and then we need to move into 3 dimensions to add smoothness in there. And we can still find a decision boundary or plane that separates the apples and orange in 3 dimensions, or we can go to 4 dimensions. And there's no limit really on how many dimensions you can go to. The main caveat for adding more dimensions is you can overfit. And overfit a model to some training data, it means that your model is not good when it comes to giving it new examples. So we say it's not good at generalizing when you give it a new example of a fruit to predict whether it's an apple or an orange correctly. Now, how many extra features can you add? Well, in image classification, every pixel in your image is a feature. Now, if you've got a high definition image or a 4K image, that's millions of features. And that might sound a little bit absurd compared to what we've been looking at, which is 2 or 3 features. But the area of deep learning, which has been massively successful in image recognition and natural language processing, typically trains models on millions of features and even millions of examples with millions of features. Now, not all features are useful. Not all the properties that have predictive power should be features either. So you can have a feature which is redundant. So you might have a similar features already there. So why add a new one? It costs more compute. It mightn't train as well. You can have irrelevant features, so pieces of information that just don't help predict. And we saw the example earlier of the weight of the fruit. It doesn't really have any predictive power whether it's an apple or an orange. The other important point, and this is something that's very important in general for machine learning practitioners, is that you need to know about whether this is a feature you should actually use when you're training models, when you want to build a prediction service that's going to predict something. Some features are prohibited, and they may be prohibited by legislation, they may be prohibited by norms, you may not be allowed to use them for whatever reason, and it's going to be context dependent. We're in a new field. AI is a very new field. We don't have adequate legislation governing what we can use as features and what we can't use. Some norms are developing, so best practices, things that you shouldn't use, for example, for features are gender or ethnicity, unless you want your model to predict based on gender, which typically is not something you want to do, because that model may be biased then towards a certain gender. And the same for ethnicity. You personally, given the lack of legislation and guidelines, you're personally responsible for the systems you build as an engineer, a developer. And it's important to think about the ethical responsibility of the features that you use. So getting back to the example of having millions of features, well, differentiating between an apple and an orange is not too hard, let's be honest about it, right? But what can you do if you have millions of features of apples? Well, there's a paper referenced here that shows you can identify if an apple has scab disease, if it has rot disease or blotch disease. And you can see here that the images shown are quite accurately finding the places on the apple where this disease has broken out. To use these kind of large data sets with rotten apples, You need to have lots of GPUs, so graphical processing units, to train your data. You'll need to have some image equipment to take the photos, and you'll need lots of examples. And deep learning models are very good at learning these non-linear decision boundaries, so they're non-linear classifiers in this case. Now, we've talked primarily about what we call classification, so taking a piece of fruit and saying what class does it belong to. Is it an apple? Is it an orange? Or even if we have an apple, we say, well, does this apple have scab disease or not? That's what we call classification. Machine learning, and supervised machine learning in particular, that we've been talking about, where we have some input examples with features and we have labels telling me what the actual thing we're trying to predict is, can also be used to predict a number. So we might want to predict, for example, the weight of an apple. So if we have 3 apples here, we can see they're different types of apple. We have a nice red apple, a Granny Smith deep dark green apple, and a light green golden delicious apple. And each weigh slightly different. So if you've eaten a golden delicious, you'll know it's quite a light apple. And then the Granny Smith's a very dense apple. And the red apple is also light. So you could also train a machine learning model to estimate the weight of a fruit given its dimensions. So maybe its diameter and its color. So the dark green, your machine learning model could infer that this particular fruit is a Granny Smith, so it's going to be quite heavy. Or if it's light green, it might be golden delicious and a bit lighter. So this is what we call regression in machine learning, and supervised machine learning can be used to train models that predict numbers. So here's another example of a machine learning problem. It's surfing, and this is something I've worked on. I find it a passion of mine. And what you want to do in this particular case is you want to predict the height of a wave at a beach, because you want to go surfing there. And out in the open ocean, we get these open ocean swells that come in. And there's 3 features that we need to care about for these particular swells coming in. We need to know the direction they're coming in. We need to know the height of the swell. We need to know the gap between the waves, so the period. You can measure that in time, typically. So, given those 3 input features, we'd like to know what will the height be at the beach. So we need to have a label. In this case, somebody at the beach can take a measurement and say the time at which they observed the height on the beach, and with enough measurements and enough features that we get from these open ocean swell predictions, we'll be able to learn to predict the height of the wave at that beach. In this case, we can see, there's some knowledge that we have that the waves at the point tend to be higher because the swell breaks there first, if it comes in that particular direction from the north. But we don't even need to know all of these small features. We can just feed in the data and the model will learn the patterns. And that's the beauty of machine learning. And in this particular problem, you could actually also ask, well, if I'm predicting the height of a wave, it should be a regression, right? Well, you can also model this with classification, because there's not that many different wave heights that are relevant to surfers. So you might say that the height of the wave at the highest will be 10 feet, and the lowest it will be 0. So if we have an accuracy of a half foot, that means there's only 20 classes to predict. So you might say in this case, classification is even a little bit easier than regression. Nobody cares if the wave is, 4 feet and 2 inches or 4 feet and 3 inches. They just know it's around 4 feet. That's good enough. So given what we've gone through, what is supervised machine learning? Well, with our apple-orange classifier, we used the features and labels to train a model to find a decision boundary. And when a new fruit arrived, we could use this model to predict if a new piece of fruit was an apple or an orange. And we can generalize what we went through with apples and oranges to say that supervised machine learning in general is concerned with extracting a pattern from labeled data. And that includes, when we say data, we mean features, to build models. And with that model, we'll be able to make predictions for new data that we haven't seen before that doesn't have labels. And that means new features, new input features. Now, if you're to be a little bit more mathematical about defining it, what we can say is in supervised machine learning, we're trying to take input features and labels, apply some training function to generate a model. So our training stage will generate a model, but it needs input features and labels. When we have the model, we can apply that model as a function to new features, and we'll get a prediction. The prediction is not the label. We don't know the actual outcome yet. It's our model prediction of what the outcome will be. Later on, maybe we'll get back the outcome, and then we can analyze whether our model performed well or not based on whether the prediction was close to the actual outcome, the real label of what actually happened. So with that, what will we cover with machine learning in this course? Well, we're going to work with building and operating the pipelines that create these features. We're going to build and operate the pipelines that train these models, build and operate the pipelines that make the predictions, and then manage all of the features and models. And we're going to do it all on serverless infrastructure. What we're not going to go into too much detail is the modeling work. So we went through a very simple decision tree example here, but there's many other courses out there that are very comprehensive in dealing with modeling, whether you're going to use decision trees or deep learning. That's kind of outside the scope of the course. We're going to learn what we can do with the models when we have them, and how do we get the data into such a way that we can use that data or features to train our models effectively and make inference with our models. So if you want to read up more on studying machine learning, there's many courses out there. If you have a programming background, Fast AI is quite good. If you've no theoretical interest really, or theoretical motivation, if you want to do more theory driven, the MIT course and Coursera are both very good. And if you want to just get started, this is a relatively good video to give you an introduction to machine learning from Google in this case. So with that, I'm looking forward to the rest of the course, and I hope you have a great time on your machine learning journey.